Today, we're going to dive into one of the most mind-bending stories in all of science, the history of quantum mechanics. And trust me, this isn't just about dusty equations. This is the story of how our entire understanding of reality was turned completely upside down, shifting from a neat, predictable clockwork universe to, well, something a whole lot stranger.
So, let's set the scene. It's the late 1800s, and physicists felt pretty good about things. They had this picture of the atom, right? A positive nucleus in the middle with electrons zipping around it like tiny little planets. But there was a huge, glaring problem. According to their own rules, classical physics, those orbiting electrons should be losing energy constantly, and that meant they should spiral into the nucleus in like a fraction of a second. So the fact that atoms existed at all was a complete mystery. It was the first major sign that the laws of physics needed a serious rewrite.
And if that wasn't bad enough, there was the ultraviolet catastrophe. Now this sounds dramatic, and it really was. Classical theories predicted that any hot object, even the filament in a light bulb, should blast out an infinite amount of energy, especially at high frequencies like ultraviolet light. We're talking deadly radiation from just flipping a switch. But obviously that's not what happens. In the real world, the energy peaks and then drops off. It was another total failure of the old physics, a clear signal that something was fundamentally wrong.
All right, so here's our game plan for figuring this all out. We'll start with those cracks in the old physics, then look at the very first clues that started the revolution. From there, we'll see how they applied these new ideas to the atom, witness the birth of a whole new mechanics in the 1920s, grapple with its truly bizarre rules, and finally, see how it all shapes the world we live in today.
So where does this new story begin? Well, not with some grand theory, but with a few strange clues uncovered by scientists who, to be honest, were a little spooked by what they were finding.
In the year 1900, a physicist named Max Planck decided to tackle that ultraviolet catastrophe head-on. And his solution was, well, it was radical. He suggested that maybe energy isn't a continuous flow. Maybe, he thought, it's emitted in tiny, distinct packets. He called these packets quanta. The funny thing is, even Planck didn't really believe it at first. He saw it as just a mathematical trick to make the equations work, not a description of how reality actually behaved.
And this is the core idea right here. Think about classical physics like a smooth ramp. You can be anywhere on it. Planck's idea turned that ramp into a staircase. Energy could only exist on one step or the next step up, but never ever in between. You can have one packet of energy or two packets, but you can't have one and a half. This concept, quantization, was the very first step into this strange new quantum world.
This whole idea gets boiled down into this simple, elegant, and world-changing equation. E equals h nu. It just says that the energy of one of those packets, E, is directly tied to its frequency, nu. And that h there, that's Planck's constant. The reason you don't notice this quantum staircase in your everyday life is that h is an absurdly, ridiculously tiny number. The steps are just too small for us to see.
So Planck hesitantly opened the door to this new reality. But 5 years later, it was Albert Einstein who really kicked it wide open. He used Planck's idea to solve another puzzle called the photoelectric effect. He said, what if light itself is made of these energy packets? These would later be called photons, and boom, it perfectly explained why hitting a metal with high-frequency light knocked electrons out, while even super bright low-frequency light did nothing. It was all about the energy of each individual packet, not the overall brightness. This was a massive win for the quantum idea.
Okay, so the idea of quanta is starting to get some serious traction. The next logical step? Taking this radical concept and applying it to the biggest puzzle of all, the atom itself.
And believe me, our picture of the atom was changing at lightning speed. We went from the plum pudding model, which is basically just electrons stuck in a blob of positive goo, to Rutherford's nuclear model, which gave us the nucleus. But remember, Rutherford's atom was unstable by the old rules. The stage was set for someone to connect the dots.
And that someone was Niels Bohr. In 1913, he took the quantum idea and applied it directly to the atom. He proposed that electrons could only exist in specific, stable orbits, like fixed rungs on a ladder. They couldn't be in between. And to move from one orbit to another, they made an instantaneous quantum jump, absorbing or spitting out a photon with the perfect amount of energy. It sounded bizarre, but this model perfectly explained the light spectrum of hydrogen, something no other theory could do.
Now, Bohr's model was a huge breakthrough, but it was still kind of a patch. It worked for hydrogen, but it wasn't the whole story. The real revolution The construction of a complete theory of quantum mechanics was about to happen in the 1920s. This was the golden age.
The revolution kicked into high gear in 1924 when Louis de Broglie came along with this just wild thought. He said, okay, if light waves can act like particles, why can't particles, like electrons, act like waves? This idea of matter waves was so out there, but it was soon proven in experiments. You could actually see beams of electrons behaving just like waves of light. It was unbelievable.
And this idea just lit a fire. Suddenly, two different paths to a full theory emerged at almost the same time. In Germany, Werner Heisenberg developed something called matrix mechanics. It was very abstract, all about particles and those discrete quantum jumps. Meanwhile, Erwin Schrödinger developed wave mechanics, which described the electron as a continuous wave. They looked totally different, they felt totally different, but in 1926, Schrödinger proved they were just two sides of the same coin. They were mathematically identical. They had found it.
So, the new mechanics worked. I mean, it worked with stunning, unbelievable accuracy. But the picture of the universe it painted, well, it was deeply weird. It forced physicists to throw out the old rulebook and accept a whole new set of principles about what reality even is.
At the heart of it are these core ideas that just mess with your head. First, wave-particle duality. Everything can be both a wave and a particle, and what you see depends on how you look. Then there's the uncertainty principle. You can never know both exactly where a particle is and exactly where it's going. And this isn't about having better tools. The universe itself has a built-in fuzziness. But the biggest one, the universe is probabilistic. The theory doesn't tell you what will happen, only the odds of what might happen. And not everyone was on board with this, especially that last part. This idea of a random, chance-based universe was just too much for Albert Einstein. He famously complained, God does not play dice. He just couldn't accept that at its most fundamental level, reality was a cosmic game of chance.
Now, the most common way physicists learn to deal with all this weirdness is known as the Copenhagen interpretation, championed by Bohr and Heisenberg. It basically says a particle exists in all its possible states at once, a superposition, and then the very act of measuring it forces it to collapse and pick one reality. Yeah, in this view, reality isn't really real until we look at it.
So, okay, this all sounds incredibly abstract. Probabilities, collapsing wave functions. Why should any of us care? Well, here's why. Because as strange as this theory sounds, it is quite literally the foundation of our entire modern world.
And the revolution didn't just stop in the 1920s. It kept going. Paul Dirac came along and unified it with special relativity, which led to the prediction of antimatter. From there, we got quantum electrodynamics, or QED, to describe light and matter, and eventually, the theories that explain the fundamental forces inside the atom. The impact is just everywhere. The transistors and microchips inside the device you're watching this on right now, that's quantum mechanics. Lasers, MRI machines in hospitals, nuclear energy, and the entire future of quantum computing, none of it would be possible without this revolution.
And just how good is this theory? It is mind-bogglingly accurate. The predictions of quantum electrodynamics have been tested and confirmed to an accuracy of 1 part in a trillion. That makes it, without a doubt, the single most successful and precisely tested theory in the entire history of science. Period.
So let's pull it all together. We went from a complete crisis in physics to a new theory of reality that is both unbelievably powerful and just profoundly bizarre. But here's the thing, the story is far from over. And this brings us back to the biggest question of all. For all its incredible success, physicists still argue about what quantum mechanics really means. It gave us the rulebook for the universe, but we're still trying to understand the story that rulebook is telling. If the world is built on probability and the act of looking at it changes it, then what is this solid, real, predictable world that you and I experience every single day? That is a profound mystery quantum mechanics leaves us with. And honestly, we're still trying to figure it out.